So let us start now. 1 minute. Can you hear me? Then you can reply on the chat box. Okay. Can you hear my noise? You have to reply in the chat box. Okay. Okay. Thank you. This is the lecture on the YouTube. I am trying to now to start the topic. Okay. So kinetics of acid-base catalysis completed by us. Acid catalyzed reaction. You can see on the screen the reaction between acid Ha and substrate S. Okay, so we already derived the derivation for this. Okay, where P is the product of the reaction and SS positive is the intermediate species. In this acid catalyzed reaction, the reaction between the substrate and this acid Ha takes place, formation of SH positive and this anion, where K1 is called as rate constant for the forward reaction and K minus 1 is called as rate constant for the reverse reaction. What is the acid catalyzed reaction? Acid catalyzed reaction is the reaction which is catalyzed by the acid. So acid is playing the role of the catalyst. So in this reaction, first of all, there is a formation of the intermediate SS positive, and that intermediate undergoes hydrolysis and product formation will take place. So as the intermediate species is unstable, in catalyzed reaction particularly, the intermediate is formed and that intermediate is unstable. So for this, a steady state approximation can be applied. We can apply the steady state approximation to this. Okay, and according to that we can find out this. Okay, concentration of the intermediate. According to that we can find out the concentration of the intermediate. Okay, so according to the steady state approximation, you can see the rate of the formation of the intermediate with respect to time, it is equal to K1 into concentration of the substrate into concentration of the acid minus K minus 1 into concentration of the intermediate into concentration of the anion minus K2 into concentration of the intermediate, it becomes equal to 0. Okay, this, the rate of the formation of the intermediate with respect to time becomes equal to 0. Okay, once again I would like to write that catalyzed reaction here. So substrate reacts with acid, formation of intermediate SH positive and anion. So K1 is the rate constant for the formation of the intermediate and K minus is the rate constant here. Reverse process, conversion of the intermediate into the reactant. Now in the second step, the intermediate undergoes hydrolysis. So there is a formation of the product. Okay. K2 is the rate constant here. So we are writing here the rate of the formation of the intermediate with respect to time. So it is equal to the rate of the formation of this intermediate. It is directly proportional to the concentration of the substrate and the concentration of the acid. And K1 is the rate constant there. So K1 into concentration of the substrate into concentration of the acid. Now reverse process the intermediate back to convert it into the substrate and the acid. So K minus 1, it is the rate constant for that, into concentration of the intermediate into the concentration of the anion. Now on the same time, this intermediate, it is converted to the product. So we have written here conversion of the intermediate, that is minus K2 into concentration of the intermediate becomes equal to 0 according to the steady state approximation. So this step is very important to understand. Once we write this step, latter part becomes easy. Okay. So in this equation now, you can see taking this minus on this side, this minus K2 on this side, and taking the common here. SS positive is common. So we can write in this way. Okay. So concentration of the intermediate becomes equal to K1 into concentration of the substrate into concentration of the acid divided by this K minus 1 into concentration of the anion plus K2. Okay. So this is the very important equation. Suppose that this is the equation 4 here. Now the rate of the formation of the product. This is the rate determining step, which is a slow step here. And always in kinetics, slow step, it is the rate determining step. So rate of the formation of the product depends upon concentration of the SS positive. So let us write here rate of the formation of the product with respect to time. It is directly proportional to this concentration of the intermediate. According to this reaction, we write this. So what is the rate constant here? K2. Rate of the formation of the product with respect to time, it is equal to K2 into concentration of the intermediate. So you can see here putting the value of this concentration of the intermediate. We already find out this. So it is K1 K2 into concentration of the substrate into concentration of the acid divided by K minus 1 into concentration of the anion plus K2. This is equation 5. Now for this equation 5, there are two particular cases are applicable. First case is that if K2 is very large as compared to K minus 1 into concentration of the anion. Once we derive the equation here, we have to apply the two cases here. K2 is very large, means this step, conversion of the intermediate into the product. K2 becomes very large. Once the intermediate is formed, it is immediately converted into the product. Means this chances of the reverse reactions are less here. Chances of the reverse reactions are very less here. Therefore, K minus 1 is very small. And K2 becomes very large. It means that this is neglected from this equation. So this equation can be written as rate of the formation of the product with respect to time. It is equal to rate of the formation of the intermediate with respect to time. It is equal to, now we can write this. Okay. Wait for some time. See here. It is equal to. So as K2 is very large, so this is neglected from this. So we can write the equation now, K1 into K2 into concentration of the substrate into concentration of the acid HA divided by this K2. K minus 1 is neglected. So K2 get cancelled here. So let us see the next step here. Already we have written case 1. If the rate constant K2 of decomposition of the intermediate, it is very larger, then K2 is very greater than K minus 1. So K2 becomes cancelled here. So it is equal to K1 into concentration of the substrate into concentration of the acid. So rate of the formation of the product with respect to time, it is directly proportional to the concentration of the acid and concentration of the substrate. So from this equation we can say that the rate of the reaction is directly proportional to the concentration of the acid catalyst, okay, and the substrate. The reaction rate of the formation of the product, it is depends upon concentration of the acid catalyst as well as the reactant. This condition is called as general acid catalysis. It is called as general acid catalysis because general acid HA is involved there. So this is called as general acid catalysis. Okay, general acid catalysis. Now let us apply the second case. If K minus 1 into the concentration of the anion, it is very greater than K2. Okay, let us once again write that process here. Substrate reacts with general acid, which gives the product intermediate, that is SS positive, and anion A minus, and this is reverse. And this intermediate, it is decomposes or undergoes hydrolysis and formation of this product. Okay, K2. K2 is the rate constant here, and here product is formed. So if K minus 1 into concentration of the anion, means this reverse process is very larger than this. Means reversible reaction, it is more favorable here than the formation of the product. So in that case K2 becomes negligible. So K2 can be neglected there from that equation. You can see the equation which has written by us, this K2 is negligible there. This K2 is negligible. Okay. Then we can write K1 K2 into concentration of the substrate divided by K minus 1 into concentration of the HA upon concentration of the anion A minus. See that. Concentration of the general acid divided by concentration of the anion. This is equation 7. Okay. Now we can find out this ratio, concentration of the acid divided by concentration of the anion. Let us see how it will be. Okay. So this ratio, rate of the formation of the product, it is equal to K1 into K2 into concentration of the substrate divided by K minus 1 into concentration of the H plus upon K. How it becomes? Okay. So let us write here the concentration of the dissociation of this general acid. Okay. The general acid, it is dissociated as HA, should be dissociated as H plus and A minus anion. So we can write the dissociation constant for this acid K equal to concentration of hydrogen ion into concentration of the anion divided by concentration of the acid HA. Okay. We can simplify this. Taking HA here, concentration of the HA divided by this concentration of the anion, just rearrangement is here. It is equal to, okay, so K should be here concentration of the hydrogen ion divided by dissociation constant Ka. So we can substitute this ratio by this term, concentration of the hydrogen ion divided by Ka. Okay, so equation 7 can be written as, in this way. Okay. Now in this equation K1 is constant, K2 is also constant. Okay, K1 is constant, K2 is constant, K minus 1 is constant, K is constant. So instead of writing all these constants, K1 constant, K2 constant, K minus 1 is constant and K is also constant. So we can write here KH positive. Okay, it is also constant. And this KH positive, it is called as catalytic coefficient of hydrogen ion, because in this reaction hydrogen ion is involved. So it is called as catalytic coefficient of hydrogen ion. This is the equation 8. So equation 8 shows that the rate of the reaction is, according to this equation now, the rate of the reaction is directly proportional to the concentration of the hydrogen ions. Okay, this. Such a condition is called specific hydrogen ion catalysis. Specific hydrogen ion catalysis, because hydrogen ion is involved in the equation 8. So it is called as specific hydrogen ion catalysis. And this equation 8 can be written as, let us write the equation 8 here. Further modification. So rate of the formation of the product divided by time dt, it is equal to K into S. It means that K is positive into concentration of the hydrogen ion. K equal to, it is another constant, KH positive, catalytic coefficient of the hydrogen ion multiplied by concentration of the hydrogen ion. It is equal to K. This is equation 9. Suppose it is constant here. So rate of the formation of the product with respect to time, it is directly proportional to the concentration of the substrate. According to this equation, it is directly proportional to the concentration of the substrate. So we know that K equal to KH positive into concentration of the hydrogen ion. Okay. Let us see here. K, this is a constant. KH positive into concentration of the hydrogen ion. You can see here. KH positive into concentration of the hydrogen ion. It is equal to K. Okay. It is equal to K here. So taking logarithm on both sides. So this is log to the base 10 K, it is equal to log to the base 10 K is positive plus log to the base 10 concentration of the hydrogen ion, or log to the base 10 K equal to log to the base 10 K is positive minus pH, because pH equal to minus log to the base 10 concentration of the hydrogen ion. According to the definition of the pH should be equal to pH, it is equal to power of the hydrogen ion, it is equal to minus log to the base 10 concentration of the hydrogen ion. Okay, concentration of the hydrogen ion. Therefore this is minus pH equal to log to the base 10 concentration of the hydrogen ion here. Okay, concentration of the hydrogen ion here. So we can substitute this on this term minus pH here. Okay, equation 10. Therefore a graph of log to the base 10 K versus pH means this graph log to the base 10 K, that is K is a constant here, versus pH of the solution should be a straight line with slope equal to -1 here. Slope it is -1 here. This has been observed for the acid catalyzed inversion of sucrose. This type of the variation is observed there, where slope becomes equal to -1, and it is according to this equation. When you are going to plot this graph, see now the graph will be like this: log to the base 10 or log of K versus pH. Okay, so in this case slope it is -1, indicates that it is decreasing value like this, and slope it is equal to -1 here. Okay, slope it is equal to -1, and this is intercept onto the y-axis. This is log to the base 10 Kh, this value log to the base 10 Kh, catalytic coefficient for the hydrogen ion. Okay, so try to understand about this. So in this way we derived here acid catalyzed derivation for, once again I would like to show this acid catalyzed reaction. We have started from this, the reaction between acid Ha and substrate S. We find out first the concentration of the intermediate by doing this process, then the rate of the formation of the product with respect to time, it is equal to K2 into SS positive. So by putting that values, concentration of the SS positive, we are getting this equation, and applying the two conditions. Applying the two conditions here. First it is general acid catalysis, and second it is specific hydrogen ion catalysis. Specific hydrogen ion catalysis. So this is about acid catalyzed reaction. Now let us proceed further. Base catalyzed reaction. Base catalyzed reaction. In base catalysis, a proton is first transferred from the substrate. Base is a proton acceptor. Okay, so this is supposed to be substrate SH, and this base accept the proton. Formation of this BH positive into S minus. Okay, so this base accept the proton here, and later on this substrate undergoes hydrolysis, formation of the product, and hydroxyl ions are also formed here. In base catalyzed reaction there is a formation of the hydroxyl ion, and hydroxyl ion is a base, or simply we can write this is a base here. Okay, this is a base here. OH minus ions means it is a base. Okay, in bracket we can write base. Okay, the substances which are giving the hydroxyl ions, they are called as a base. For example, NaOH, it is a base. KOH, it is a base. And according to the Lewis concept, base is a proton acceptor and acid is a proton donor. So it will accept the proton from this formation of this intermediate and this anion. And this anion undergoes hydrolysis, formation of OH minus and product. This product get formed here. Let us see the equation for this, where P is the reaction product. The ability of a base to catalyze a reaction is directly proportional to the concentration of the OH minus ion. The ability of a base to catalyze a reaction is directly proportional to the concentration of the OH minus ion. So hydroxyl ion is very important. So for the reaction catalyzed by OH minus ions, an equation similar to H plus ion in previous equation. Okay, H plus ion catalyzed reaction can be written. See here equation 10. 1 minute. Equation 10 you can see. This is the equation 10 here. Okay. So similar to equation 10 we can obtain here the equation 10 in this way. K equal to KOH minus into concentration of the hydroxyl ion. Similar to this. K equal to KH positive into concentration of the hydrogen ion. Where KH positive it is called as catalytic coefficient of the hydrogen ion. So similar to this now, this K becomes equal to KOH minus into concentration of the hydroxyl ions. So not necessary to derive all the equations here. So this for base catalyzed reaction we can write the K constant here equal to KOH minus ion into concentration of the hydroxyl ions. Now we know that KW it is called as the ionic product of water. And this ionic product of the water becomes equal to concentration of the hydrogen ion into concentration of the OH minus ion. Okay, see, water undergoes dissociation, very small dissociation of the water, H plus and OH minus ion. Actually, dissociation of the water becomes very less. So we can write here Kw, equilibrium constant for the water, it is equal to concentration of the hydrogen ion into concentration of the hydroxyl ion. Okay, so water cannot be considered here. We cannot consider the concentration of the water. So Kw it becomes equal to this. So concentration of the hydroxyl ion it is equal to Kw upon H plus ion. Okay, so we know that. Let us put the concentration of the hydroxyl ion here, K into KOH minus ion, catalytic coefficient for the hydroxyl ion. Because OH minus ion is a base and it is a catalyst here. In the previous reaction, H plus ion is a acid and it is a catalyst there. So according to the equation, that is K equal to KH positive into concentration of the hydrogen ion. So we can write this equation now, K equal to KOH minus ion into concentration of the hydroxyl ion for base catalyzed reaction. But we know that Kw becomes equal to this. So concentration of the OH minus ion it is equal to Kw divided by concentration of the hydrogen ion. So put that value here, Kw divided by concentration of the hydrogen ion. Now taking the logarithm. So this is log to the base 10 on both sides, log to the base 10 KOH minus ion plus log of Kw minus this log to the base 10 concentration of the hydroxyl ion. But this is nothing but pH equal to minus log to the base 10 concentration of the hydrogen ion. So we are getting this equation here, log to the base 10, okay, it is equal to log to the base 10 catalytic coefficient for the hydroxyl ion, log to the base 10 Kw plus pH. In this case, a graph of this y-axis log to the log K, okay, against pH, this will be a straight line with slope plus 1, like this. Positive slope is obtained here. Positive slope is obtained here. So similarly, we can derive here the equation for base catalyzed reaction. It means that K value will be increases as pH will be increases. Okay. And in the previous case, K value will be decreases as pH will be increases. So this is about base catalyzed reaction and acid catalyzed reaction. Then let us see the mechanism and kinetics of enzyme catalyzed reactions. Enzyme. So what are enzymes? Enzymes are the nitrogenous organic substances. They are known as enzyme, complex nitrogenous organic substances. Enzyme plays a very important role in the chemical reaction. They are playing the role of the catalyst. They are playing the role of the catalyst. So you can see here this reaction. Conversion of starch into maltose sugar by the enzyme distates. Conversion of maltose sugar to glucose with the help of the enzyme maltase. Conversion of glucose to ethanol with the enzyme zymase. Okay. So in every reaction there is an enzyme is involved. So enzyme playing the role of the catalyst. Let us see now the kinetics of enzyme catalysis. Kinetics of enzyme catalysis. Okay. So let us see kinetics of enzyme catalysis here. See here, 1 minute. I would like to see. Okay. So can you see on the screen? Please reply or write something in the chat box. We have completed acid catalyzed reaction and base catalyzed reaction. Now you should have to be right in the chat box where you are listening to me. Anyone? Samir Jadhav, can you hear me? Samir Jadhav. Yes. 1 minute. Anyone can reply. Can you hear me? Bhushan? Bhushan Deshmukh. Yes. Okay. So you have replied. I think you are in the lecture. So I just want to verify where you are in the lecture or not. Okay. So let us going to be continue this now. See here. Okay. So kinetics of enzyme catalysis. That what are enzymes? Enzymes are complex protein occurring in living cell. Without enzyme, there are some biological processes are takes place in our body. So enzyme playing the very important role. So what are enzymes? Enzymes are complex proteins occurring in living cell. Generally in the living cell they are present. So Michaelis and Mentine studied the kinetics of enzyme catalysis. So let us see if E is an enzyme and S is the substrate. Then according to Michaelis-Menten mechanism, E is the enzyme, S is the substrate. Formation of this intermediate ES, where K1 is the rate constant for the forward reaction. Whenever we are using the catalyst, there is always formation of the intermediate. Always there is the formation of the intermediate. So E is the enzyme, S is the substrate here, means reactant. First of all, there is a formation of the intermediate ES, or it is also called as addition complex. And this addition complex or intermediate undergoes decomposition and there is a formation of the product. So first step is reversible, second step is irreversible. So in this mechanism, ES is an addition complex, P is the product. Now the rate of the formation of the product is proportional to the concentration of the ES. This in the second step there is a formation of the product, that is the slow step, rate determining step also. In the chemical kinetic, always the slow step, it is the rate determining step. And according to that, we can write the rate of the reaction. So in this case, rate of the formation of the product. Rate of the formation of the product. With respect to time, it is directly proportional to this. It is directly proportional to this concentration of the ES, that is addition complex or intermediate. So we can write this rate of the formation of the product with respect to time, it is equal to what is the constant here, K2. So K2 into ES. This is the rate equation for the formation of the product. You can see here. Okay. So we can see this is equation 1, this is 2, this is 3 now here. Now during the course of the reaction, the concentration of the intermediate remains practically constant. This. So according to the steady state approximation, we can take on its concentration becomes equal to 0. The rate of the formation of the intermediate with respect to time. This rate of the formation of the intermediate with respect to time becomes equal to 0 here. Okay, so you can see here it becomes equal to 0. So let us write down this concentration of the intermediate with respect to time here. So I would like to write here concentration of the intermediate with respect to time dt, it is equal to, okay, it is equal to here, see, es will be formed here, k1 is the constant for this, so k1 into es, sorry, k1 into concentration of the E multiplied by concentration of the S, concentration of the enzyme into the concentration of the substrate. Now in the reverse process it is get back converted, minus k minus 1. Okay, we are writing here the rate of the formation of the intermediate, but now in the back process it is converted into the back to the reactant. So k minus 1 into concentration of the ES, a concentration of the ES. Now in this case also it is converted to the product, so conversion of the intermediate into the product. So take here minus sign here because it is converted here. In the case of the formation there is a positive sign, and in the case of the conversion, decomposition, it have the negative sign. Okay. So we can take the common here. Let us see, proceed further. See, the steady state equation is rate of the formation of the intermediate with respect to time, it is equal to k1 into E into S minus k minus 1 into ES minus k2 into ES. ES is common here, you can see. So in bracket we can write k minus 1 plus k2 into concentration of ES becomes equal to 0. Now in this process, the total concentration of the enzyme is E0. When we start the reaction, we have taken E0 here. So this E0 becomes equal to the concentration of the free enzyme and the concentration of the addition complex. This initial concentration of the enzyme, suppose that it is E0. So E0 it is equal to concentration of the free enzyme E, and enzyme goes into the intermediate, that is ES. This is the first step. Let us write that once again. Concentration of E plus S gives ES. Okay. So total concentration of the enzyme becomes equal to concentration of the free enzyme into the concentration of the ES, enzyme into the intermediate. Because all the enzyme cannot be utilized, some quantity will be free. Therefore, we can write here concentration of the free enzyme becomes equal to remaining quantity. Concentration of E0 means initial minus concentration of ES. Okay. So you can see here concentration of the free enzyme becomes equal to this. So let us substitute this equation now into this. Here concentration of the enzyme becomes equal to this. So we can modify this equation now. So that equation can be written as K1 into concentration of E. It is now E0. Suppose that it is in bracket minus concentration of the ES into concentration of the substrate, bracket complete, concentration of the substrate, and remaining quantity will be as it is. So this can be simplified as concentration K1 into concentration of the E0 into concentration of the substrate. This separate the terms here, minus K1 into concentration of the ES into concentration of the substrate. Okay, and remaining term will be this. Okay, minus K2 into K minus 1 plus K2 into ES. So we can simplify this term now. So it is equal to now this by putting the concentration of the free enzyme according to this. We have substituted here this. So we can write this equation now. Now let us take this on this side, right side there. Okay, so you can see here. So K1 into concentration of the substrate into concentration of the E0 minus this. Okay, so we can simplify this. So this goes, this is having minus sign here. Es is there, Es is here. Once again, we have to take the common Es, and this is goes to this side positive. So K1 into concentration of the substrate into concentration of the E0 becomes equal to this K1 into concentration of the Es plus concentration of the substrate, and this is remains as it, K minus 1 plus K2 into concentration of the Es. Es is common here. Okay, taking Es is a common. So we can write this now. Let us see. Okay. See here. Es is common here. You can see this Es is common. This Es is common here. So we can write here. Just you have to see K1 into concentration of the substrate. Okay. Plus K minus 1 plus K2. Okay. Into concentration of the Es. Okay. Es is common here. So concentration of Es equal to, this is on to the left hand side, K1 into S upon E0 plus K1 into concentration of the substrate plus K minus 1 into K2, plus K2. This is supposed to be, let us give the number into this equation. Okay, this is 3. Now let us see, this is 4, 5, 6, then this is 7, and this is 8 now, equation 8. 18 is 8 here, equation 8 here. So give the number to this equation 8 here. Okay. So we are getting concentration of the intermediate Es becomes equal to, now we know that the rate of the formation of the addition complex Es will be given by, we have already written the rate here, that is rate of the formation of the product with respect to time, it is equal to, this is rate, it is equal to K2 into concentration of Es, and we find out here Es. So to find out Es, we have done this whole process previously. So concentration of the Es, it is equal to, now put here Es into this equation. So reaction rate or this rate of the formation of the product with respect to time, either we can write this or reaction rate. So it is equal to K2 into, by putting this value now, K1 into concentration of the substrate into concentration of the E0, K1 plus S, K minus 1 plus K2. So this is K1 K2 into concentration of the substrate into concentration of the E0 divided by this denominator does not change here. K1 into concentration of the substrate into K minus 1 plus K2. This is equation 9. Okay. So we are getting here rate of the formation of the product with respect to time, that is reaction rate, becomes equal to this. Let us apply the cases to this equation. Two cases are there, I think. Or we can simplify this equation first. Dividing by K1 to the numerator and denominator. Dividing by K1 in equation 9 to the numerator and denominator. Divide this numerator by K1, divide this denominator by K1. So K1 is cancelled here. So it is K2 into concentration of the substrate into concentration of the E0. K1 is also constant here, only this is remaining. And this is K minus 1 plus K2 divided by K1. You can see here. See, reaction rate, it is equal to, we are getting this equation, K2 into concentration of the substrate into concentration of the E0. K1 get cancelled here, concentration of the substrate plus K minus 1 plus K2 divided by K1. K minus 1 is constant, K2 is constant, and K1 is also constant. Okay. So instead of taking this, we have to take the another constant here, Km. And this Km is called as Michaelis constant. This Km, it is called as Michaelis constant. Okay. It is Michaelis constant here. So we are getting equation 21. Reaction rate becomes equal to, okay, K2 into concentration of the substrate into concentration of the enzyme, initial concentration of the enzyme divided by substrate plus Km. This equation is called as, give the number into this equation now. This is supposed to be equation 9 here. So this equation 9, it is called as, this equation 9, it is called as, you can see, Michaelis-Menten equation or Michaelis-Menten law. Okay. Two particular cases can be considered here for this equation. Two particular cases. Once again, I would like to write that equation here. Okay. See this equation. Reaction rate equal to K2 into concentration of the substrate into concentration of the E0. Okay. K2 into concentration of the substrate. Reaction rate becomes equal to, okay, reaction rate, it is equal to reaction rate, it is equal to K2 into concentration of the substrate into concentration of the E0 divided by concentration of the substrate plus Km. Okay, this equation we have written here. See now, when concentration of the substrate is very small, first condition, it is neglected from this equation. Okay, as compared to Km, this constant, this S becomes very small in the denominator. So in the denominator of this equation 9, okay, of this equation 9. So concentration of the substrate can be neglected here in the equation 9 here. Concentration of the substrate can be neglected here. It is very small. So equation can be written now in this way, K1 into this divided by Km. From this equation, it follows that at low concentration of the substrate, this low concentration of the substrate means, once again let us write that reaction, E plus S gives ES, low concentration of the substrate. Okay, the rate is directly proportional to the concentration. Rate is directly proportional to the this concentration, and the reaction is first order with respect to the substrate. Reaction is first order with respect to the substrate. If the concentration of the substrate becomes very small, then the rate is directly proportional to the concentration, and the reaction is first order with respect to the substrate. Okay, this is first condition. Let us see now the second condition. When the concentration of the substrate is very large as compared to Km, so Km is neglected. Km is neglected from this equation. Okay, so we can write the equation now. So substrate get cancelled there. Rate becomes equal to K2 into E0. You can see Km is Km becomes very small here as compared to this. So this can be neglected. So this get cancelled here. So it is K2 into E0. The reaction rate will be constant, and hence the reaction will be zero order. Does not depends upon. Okay, if we cannot consider here the concentration of the enzyme. So it means that the reaction does not depends upon anyone. So the reaction rate will be constant, and hence this is constant here. K2 is constant. Hence the reaction will be zero order. And previous reaction is first order. But when it is possible? If the concentration of the substrate is less, then reaction rate is proportional to the concentration of the substrate. If the concentration of the substrate is very large here, so from the denominator you cannot neglect S here. Okay, you cannot neglect this. Okay, so in that case reaction is not first order. So the condition is that for the first order reaction, the concentration of the reactant should be less, and the reaction rate should depends upon the concentration of the substrate. Okay, thus it can be seen that enzyme catalyzed reactions are similar to surface reactions in which the rate is proportional to the concentration at low concentration, and it is independent on the concentration of the catalyst at high concentration, so it is zero order. So this is about the enzyme catalyzed reaction, kinetics of enzyme catalyzed reaction. Once again you have to see it, kinetics of enzyme catalyzed reaction, how we derive the equation. Just overlook here. Okay, just overlook here the equation. See, we find out concentration of the ES. This step is very important, and we have to substitute that concentration of the ES here, and we have to write the reaction rate. Okay, and we can simplify this by dividing K1 to the numerator and denominator, and we introduce here Michaelis-Menten constant. So this is the rate equation. Rate of the formation of the product with respect to time becomes equal to this. And for this rate equation, we apply the two cases. First case is that concentration of the substrate is very large, very small. Then it can be neglected from the denominator. Okay, so K2 is constant, Km is constant. So reaction rate is proportional to the concentration of the substrate at low concentration. Okay, so it follows the first order, directly proportional to the concentration. Hence it is first order. And if the concentration of the substrate is very large, means concentration of the reactant is very large, then the rate of the reaction does not depend upon the concentration of the substrate. If it is very large, it means that K2 is constant. The reaction rate will be constant. At certain stage, the reaction rate will be increases. Later on, it cannot be increases. Even though we are going to increase the concentration of the reactant, but the rate of the reaction does not increases. It means that K2 is constant here, and the reaction rate will be constant, and hence the reaction will be zero order. It should be zero order. So this is the kinetics involved in the enzyme catalyzed reaction. Enzyme catalyzed reaction. Okay. So in this way, we have completed this topic, that is acid catalyzed reaction and base catalyzed reaction and enzyme catalyzed reaction. Okay, so this is the very important topic. Okay, so I expect you understand this topic. Now I would like to stop here. I think time is already 1 hour has been completed. So I want to stop here the discussion. Okay.